Got it.
There we go. So welcome everyone to, let's see here, to the September meeting of the Seattle Robotics Society. Let me get to the right set of slides here. And it's not those, it's these. So why is it? Oh, that's weird. Why is it asking me that? Did I click the? Oh, I know. I clicked the wrong button. Doggone it. September meeting. There we go. All right. Well, welcome everyone. I'm glad you guys could join us. It's cool having people from all over here. We got Josh from Boston, right? Yeah, and we got Dave Anderson from Dallas. You're actually in Dallas there, Dave?
Oh, well, I'm actually in Denton, which is about 30 miles north of Dallas. But,
well, okay. We'll give you credit for Dallas. So
Doug and Carl are both from Dallas. They're both from Dallas.
Excellent. So and yeah, and I don't know if anybody else from far off places, but if so, welcome, and we're glad you guys could join us. And
I'm from San Diego. Always happy to attend these.
Yeah. So reading message says a kid something like 40 years ago in Oregon. It was building first robot. My dad. Cool. Yeah. So welcome everybody. This is the here's the agenda we're going to start. Like I said, we're recording these meetings. We'll post them to our YouTube channel, and there'll be links in the you can go to the SRS website, and then there's a weblog where I include the slides, the chat notes, and then link to the YouTube video. So feel free to jump onto those if you like. Late down the road, probably take me, give me a week or so to get it up there, maybe less if I feel ambitious. Do share whatever you have in the Zoom chat, because that will be captured and posted. And if your microphone isn't muted, please do so unless you're actually directly sharing. And so, and if you got any ideas or whatever, you can shoot them to me at Seattle Robotics Society at Gmail. You'll see that pop up a number of times on the slides here to come. Which is what I'm just, yeah, okay. So yeah. So anything the recording will continue until after the presentation and the workshop, if we have one, or the discussion time. We won't be recording that. So, and let's see, I've mentioned this a couple of times now. I'm hoping to hear from Kevin Ross regarding a new location. I'll be pinging him to see if they've chosen something or if they're in the process of choosing something, but hopefully in the next month or two, we'll be have a place where we can start doing in-person meetings again, and our plan is to continue doing these Zoom meetings alongside that. So those of you that are coming in from far away can be able to continue to join us. So let's see. Okay, and I will probably need a little bit of assistance with that. So those whoever happens to come to the local meeting there, I might recruit you to do a little bit of computer or administration in the background to help ease the load here for me. So I'm going to be counting on people for that, and that email at the bottom there, if you know for sure you want to do that, appreciate you letting me know. But recognize that if you're sitting in a seat, you're liable to be volunteered. So community outreach, I'm going to be starting to do some computer classes this next week, again with some junior high kids. And did that last year. It was great fun. I will probably, I used the two kits that you see pictured there were the two robot kits that I used. I'm looking at some other stuff. I know Dave suggested mBot, which is another kit that's pretty geared nicely for kids. So I'm looking at some options, and I want to get more into programming with the kids on these things, because we did a lot of stuff where we hands-on building, and the kids took the little black robot with the camera on top of it there. I added some hardware to it to allow Legos to be, Lego bricks essentially, to be built on top of that. Kids had great fun with that, but we found the built-in programs were a little deficient, and some of the remote control stuff didn't work too well. And I really love to get into showing them some options for how to make that stuff better, you know, and start to teach them a little bit about programming. So I'm looking forward to doing some of that this coming year. If you're not aware of it, here in this coming week, well, actually it starts the 25th, although there's already been a couple of events, but Drive Electric Week, promoting electric cars of any and all types, homebrew, do-it-yourself, conversions, you name it. And I'm planning to be at an event up in Mill Creek, which is way up north, about 50 miles north of where I live. I live in Federal Way, so I'm almost to Tacoma, and this is like almost to Everett, so it's like at the opposite side of Seattle. Looking forward to that. So if you have any any particular questions, you're welcome to ask, or you can visit Drive Electric Week, and they have a calendar of events across the country. Stuff is happening everywhere, so the in-person events are starting up again here. The last year when they did this, everything was virtual, and I don't know, that just not the same thing, not the same thing. And coming up a little bit later, we are going to have Josh Pieper. Is that correct, Josh? Is that how correct way to pronounce your name?
Pieper, doesn't matter though.
Pieper, okay. Who is a CEO of mjbots, Robotics Systems, is going to be sharing with us about this very cool four-legged robot that probably reminds you a little bit of somebody else's robot out there. And he's going to be sharing about that guy and answering other questions. And if you have questions, particularly about starting and running your own robot company, this would be the guy to ask. Let's see. So online presenters, I'm always interested. International presenters are a possibility depending upon where they are located. And so we can always talk about that. But if you come across interesting looking presenters, let me know and I can reach out to them. And also, because that's supposed to say your project, not your projector. If you have your own project that you would like to share with the group, please reach out to me regarding that as well. So I'm always interested. In the February 2022 meeting is going to be a late afternoon. It's a one-time late afternoon meeting to accommodate a presenter in Japan. So he's going to be presenting to us live from Japan. And so that he doesn't have to do that at 3 o'clock in the morning, I agreed that we would move our meeting to the middle of the afternoon so that he at least has a reasonable time of day to be able to do this. And he was willing to accommodate that. So this is the lineup that's coming here. Josh will be presenting to us a little later today. We've got some other folks out there that have companies as well. And a lot of interesting things coming down the pike. And then February, of course, it'll be our special one-time afternoon meeting. And then some other things I'll continue filling in through next year. So those of you that know Robert Kellogg, he's a Pacific Northwest local. He's been shooting me gobs and gobs of suggestions, and so it's like I have a hard time keeping up with them. He shoots them at me fast, almost faster than I can contact him. But he's been very helpful in just coming up with people to present. So a special thank you to him. And discussion forums, of course, this is a kind of I typically find these to be good fillers if I can't find a presenter, but the topics are just interesting enough, even just to make them a standard thing. I like to do 1 or maybe 2 a year at least. where we just have a facilitated discussion about these topics. And if we can find somebody that has some expertise to facilitate that, that's great. But I'm willing to just kind of guide the general discussion, and then, you know, let you guys ask questions, and you know, we just kind of meander around these interesting topics. So if anybody has any other suggestions or ideas for things that we should talk about, I'd appreciate you letting me know. Robothon, our virtual Robothon exhibition, I am going to let Lloyd jump in on this one.
Yeah, so I don't know how many people attended our first Robothon exhibition about a month or so ago. That went really well, we thought. So we're going to do another one. It will be on November 13th. And let me throw a link to the page in the chat window. We have, it's going to be basically the exact same format and exact same thing that we did before. It'll be online. There will be, we're shooting for 6 presenters. That time frame worked about right, and it'll be about 2 hours-ish, maybe a little more in length. We have 2 presenters already, and we will cap it at 6. So it's one thing we noticed the first time is we don't really want to go 3 or 4 hours. That would be too long. We're just going to keep running more events. So if you want to get on the agenda for the next event, go ahead and sign up at that link. And yeah, just stay tuned, and we'll do this on November 13th. Okay. Oh, and if you didn't see the first one, we did video it, record it, and that's on the Seattle Robotics YouTube channel.
And I think, if I'm not mistaken, I think you can get to it from the SRS website or from the Robothon website. So. Okay,
cool. I don't have that link handy at the moment.
Yeah, it's if you search on YouTube for SRS clips -n -more, you'll find the video, and there's you'll find the meeting videos there as well. So, okay, just briefly on the kits that the club kits that we have available. I believe I have one of each of these, the Arduino and the Parallax propeller chip based kits. So it's a little, I mean, and since we're not doing the in-person meetings, it's a little bit tricky to arrange for somebody to get one of these, but you know, if you reach out to me at the email below there, and we can work out a meetup arrangement here in the Pacific Northwest, it can get you one of these kits. So the propeller chip is pretty cool because it's got 8 cores. You can run 8 different programs simultaneously. $135. That's all inclusive. Ideally, pay with a credit card. And then the basics, the Arduino Uno, pretty simple, good low end, kind of an entry point kit. And both of these kits are equipped especially for our club. They have some additional sensors in them that are suitable for the kinds of contests that we often do at our Robothon events. So that's option for building robots to compete. So just something to keep in mind and consider. Let's see, and we're, you know, since we're not meeting in person, can't really do, you know, a real hands-on workshop type of a thing, but we do continue after the meeting. You can ask questions, we can talk about whatever, and so I usually continue that. I'll stop the recording at the end of the meeting, but then we can continue. Depending on what I'm doing, I may or may not be able to continue to stay, but we have a Zoom subscription that can go on as long as we want. I think I don't know if we're limited to 24 hours or something like that. So, you know, if you get really into it, you could just keep going. And so with that, I am going to open it up to around the room, around the web, around the whatever, if you want to, whatever you want to call it. You've got something to share, project that you're working on, questions, whatever. now is a great time to do that. And so I would say, you know, if you got something you want to show us, go ahead and unmute and jump in. Share your desktop if you'd like, or your camera if you like.
I can give an
Go ahead. Please.
yeah, I can give a brief update.
Okay.
So I'm on ARM version 3. I still don't have it moving, but right now the focus has been on the driver, the electronics to drive the stepper motors. And I had decided to go down the path of having one processor that was going to integrate interface with all of the components on the ARM, all the sensors, the stepper drivers, the CAN bus, and had settled on using the SAMD21 64-pin version. But those that know me know that I don't like putting too much onto one processor. So I've since then modified the plan. It's going to use 2 SAMD21 processors with smaller pin counts. And I've ordered, designed and ordered 2 circuit boards. One, this is not the real thing, but one that I'm calling the driver. It will have sockets for the Pololu style stepper motor drivers, and some voltage regulation in the middle. It's got the SAMD there in the center, USB bus, reset button, programming port, and so on. And then another board, this board, also with a SAMD, that a CAN bus, voltage regulation, interface to all of the sensors, and that will then plug in essentially right over the top, leaving room for those Pololu style drivers to breathe. And I'm expecting this to come next week, and hopefully when I solder it up, it works, and then I can turn my attention to the software for that. Those that attended this meeting last week saw that I built a printed circuit board cutter. I tend, when I order these printed circuit boards, this is what I actually ordered for one of those, because there's, you know, you can get up to 100 millimeters by 100 millimeters for the same price. So I always tend to fill in around the sides with other project boards or other little doodads. And I use that cutter then to cut them apart. So I've got the cutter. I always order a solder mask, and then I have to place the parts, obviously. And the other kind of related project that I'm working on is making a hot plate for doing the reflow. Around here somewhere, I have, you know, a Value Village oven, toaster oven, which I intended to use, but I like to get up close and watch it happen. So I've changed my mind. I'm going with a hot plate. I bought an inexpensive cast iron top hot plate, and then got a 1/4 inch piece of aluminum to help spread out the heat a little bit better. And I'm now working on getting a couple thermocouples, and I'll put together a little circuit to control that. And I'll hopefully have the reflow part of it covered. Up to this point, I've always used air approach to doing reflow, and it works. But these are bigger boards than I've ever done before, and use hot air is a very tedious to sit there and just it approach. I could set up.
So, hey, Greg, I'm really happy to see that you're going with a hot plate because it's so much fun to be able to watch that up close. I also found that using an actual cast iron pan, especially a small one, if you can find a small one with high sides, it seems to me like that works better. And I think it's because some of the heat from the side of the pan hits the top of the board and irradiates the
We lost you there.
from the. Oh, sorry. Can you hear me okay?
Yeah,
Yeah,
we can
so
now. I think you were saying that the sides radiate the heat back.
Yeah, it seems like that actually makes it reflow a little bit more evenly. Or maybe it's just the cast iron, I don't know. But I now have allocated one of my wife's smallest cast iron pans to use for reflow. And I find that it works better than a flat metal sheet. Although the flat metal worked fine too.
Well,
anyway,
I mean, I could always probably put this slab of aluminum in the bottom of the cast iron and.
Yeah, it's same idea. Or make something with sides that get hot. You know, I don't know. Maybe it's worth a little welding project if you're into that. Hey, well, I wanted to.
Go ahead.
No. That's not good. Welding.
Well, I would spend hours doing it, or I could go to Goodwill and for $5 get a pan.
Exactly. Yeah. Hey, I want to make a pitch real quick for this little cardboard combat robot for people who are teaching classes with kids. This is something that we came up with a while back, which we had the idea that we wanted to make it really popular for kids to get into robotics. And we thought that one of the ways that we could make it more popular is if we built a arena. So we have, you know, Lexan sides and a piece of a little arena, and eventually we built a top with lighting and all that kind of stuff with timers. And we made these with the Node MCU, the little ESP8266. I don't know if anybody's played with those, but they do Wi-Fi and will serve web pages. You can actually program this thing to serve web pages. And these are available if you buy them from China for like $2-3 a pop, $8 on Mauser or DigiKey, or you can buy them from Amazon from good reputable sources. And they're programmable with the Arduino IDE with a little bit of tweaking on it. And this was the first version with these cheap DC gear motors. And then we went on and made other versions that used servo motors. And then there's a channel for an ESC. You can put like a regular RC motor on there. And this was one of the weapons that a guy came up with, 3D printed with a bunch of screws in the front. And here's another one. Same guy made this one, but it's a drum weapon instead. So you can see the little RC motor up here in the belt that was running it, and then he has his gear motors running everything there. You'll notice some of these look a little bit the worse for wear. And that's because we put them in the arena and battled with them. That is after on that particular robot. But the cool thing now, so this particular design is fairly. It takes a little while to put together, but most of the robots were actually not quite that complicated. That's Jordy, one of our guys who makes them, and this is Mark. Mark takes everything to the absolute extreme, and he made the most horrible killer robot imaginable within the rules. That's a spinning disc with a RC motor directly connected to it. It's at an angle there because that thing is spinning so fast that the gyroscopic precession lifts it off the ground whenever he turns it. This is the STD, single tooth disc. And not all of them were combat bots. You know, people made art bots, and people made just the simple cardboard bot. A local manufacturer made these boards to make it really easy to plug the servo headers in, and I've now made an adapter board that makes it really easy to plug servo headers into any microcontroller, really, but specifically targeted for the ESP8266 and ESP32s. And these, you know, again, just goes together. It's a couple of servos, you know, hot glue the thing together, and a kid can have that up and running in short time. And then if they go in combat with it, and it gets destroyed, it's no big deal. Most of the time the electronics survive, and you can just, you know, cut out another body, put it back in there. These are for a Sumo Bot competition that we did. And this is a way that you can bodge together a servo connector off of the digital pins on this is the Node MCU version of the ESP8266, and just pulling the battery power over here into the power and ground rails, and then you can just plug in servos on the side. Like I said, I've made an adapter board that makes that a lot easier, because that's some pretty tough soldering. It's small. We made a few of those with some groups. There's a 3D printed body that uses the same thing. You can see it there, a little canine. And then we did a steampunk event where we took the same cardboard bots, but then we added some 3D printed parts like the cow catcher and the fake pistons and boiler and stack and all that. And some guys that are really good with doing art distressed it and made the cardboard look like metal. So that's the same thing. And some kids playing. Kids love this thing. Really enjoyed it. So what I wanted to point out, though, the reason why it's really good is because the main thing is because it's a web server. It actually serves up a web page. So this control panel that you're seeing right here, this is actually a web page. So you don't have to install an app in your cell phone, and you can still control it. More than that, you can actually, another web page that the robot can serve is a editor. So you can edit the files on the robot using a web page on your tablet or your PC or whatever. And then you can reprogram the code that's in this web page. So for example, one of the things that we did was we added ping sensors to it. So I don't know if you can see it in that frame, but let me get to where I zoomed in a little bit. Yeah, so you can see that there's, 5 centimeters. So the robot is sending information from its sensors back to the phone, and then the JavaScript code that's running in the phone can react to that. So instead of just becoming a remote control robot, which is what this right now with this web page, it actually can have some smarts. And so one of the things that we did was we put in a collision avoidance system. So whenever the ping sensor detects that it's too close to an object, it takes whatever steering input you're providing and biases it to the side. So you can't hit something, right? And then you can do the opposite of that for combat mode, where it takes whatever your driving input is, and when it sees an object, it steers towards it. It always wants to go into the object. And there's bumpers here. This 111. This is there's 3 I/O pins, and it's reading the values off of those I/O pins, so you can hook those up to different devices. And I guess that's it. I have somewhere I have a video showing the self-driving thing, but I couldn't find that in short order. So again, the big advantage of it is that it allows you to have not only the regular programming via the Arduino and C code, but it also then supports the programming of what's going on inside the cell phone. And one of the things that I'm not doing, and I would love some help with, is we aren't able to access the sensors in the phone from the web page that's served from the robot, because the phones lock out HTTP non-secure web pages. They won't allow a non-secure web page to access like the camera and other sensors in the phone. So we want to upgrade to the ESP32 so that we have enough horsepower to serve HTTPS web pages from the robot, and then we'll actually be able to access the cell phone's sensors. And the idea there is to actually just set the cell phone on the robot, and then you have a fully autonomous robot with the power of your cell phone communicating with the robot via Wi-Fi through a web page that you can edit from the cell phone or from a tablet or whatever. I think it's a really exciting project, and I would love to see more people get involved in it. This is the repo, full documentation on how to use it, the onboard editor, which is based on ACE. Now, there's a little animation engine that you can put in there, so even if nobody's controlling the robot, it'll play back an animation. And then we've added sensors, and so anyway, I'll stop there, but I think it's a cool project. And I did post the link in the chat actually, but I will do so again. You're muted, by the way.
Yeah. I didn't step back. I just kind of looked at what I could see, and I didn't see it. But I figured you're good about that. So, all right. Well, thank you. That sounds pretty cool. I love projects like that. So, anybody else? Got something out there to share?
Yep. Hi everyone. So I'm Jibin. I just moved recently to Seattle. I am a senior system software engineer at NVIDIA. And I had this idea that I'm just started to build. It's basically, am I audible?
Yeah, a little bit quiet for me, but yeah, maybe sit a little closer to your computer. Okay, go ahead.
All right, I'll try to speak a little louder. So I basically had this idea that I started building primarily because my parents are old and they tend to forget to take their medicines regularly. And that's something that me being in the US, I find it hard to monitor when they are in India instead of like calling up and all. So I came up with this idea that I wanted to build. Let me try to quickly share the screen.
Okay.
Right. All right. So if you guys can see it, I just made like a design of it. I haven't actually made all of it, but I just started like getting the parts and all of that. And so this basically is like a pill box. What it does is, let me just quickly show you. So there is like a set of box, like compartments inside these. So I want to 3D print this entire thing. And there's like a set of compartments inside this where you can actually load different pills. And if we see the mechanism here, it's basically a suction motor that's something like this. With like a earphone bud that I used as a suction cap. And this can pick up a variety of pills. That's something that I tested, especially the ones that my parents are using. And the idea is basically to have like a small servo motor attached to the other end with an arm so that I can actually pick pills from this, like pills from various boxes. And here there would be like a dispenser, which would be like a cup that can be used, and rest of it is all software within like a Raspberry Pi Zero, which can basically like trigger alerts and trigger these systems to like pick the number of pills that are actually needed according to the frequency that my parents would want. So this would have like an alarm or some sound system or like, connected to Google Home or something like that, so that it would alert them at the right time to just eat the pills that are there in the cup at whatever time they want to take it. So I wanted to fabricate this and like at least make a like proof of concept sort of system, which I could take home the next time I go to India. And that's something that I don't know if it interests a lot of people or not, but that's something that I needed some help with because I'm not having right away access to a lot of the fabrication stuff like 3D printing. And I would also like to get like some expertise from people on how to, like put together all of this in such a manner that everything works, right? The idea of like, for example, I want to make it so simple so that in case it works for my parents, I'm pretty sure there are a lot of old people out there who don't take their pills on time, right? So if it works for them, then I want to make it into a little more like a better, like a full-fledged product, which can be, reused and like used by a lot of people. For example, that's why this design, if you take a look at it, I made it in such a manner that this is basically pills that are in a box which is fed by gravity, right? So the pills will always be available at the bottom. And this gripper that I kind of like tested sort of works with almost all kinds of pills. So it's sort of agnostic to the shape of the pills, for example. And the idea of making it really small so that like this, so it should ideally contain just a base cap, like a top cap, and that should be about it. Like, so you just load the pills into this, and then you set the frequency of the number of pills to be taken from which slot, for example. And then once all of that is done in the software, the servo motor would have like an arm and a small mechanism to like go down into the pockets and take the right pills. And just with that, it should be like cheap and easy to manufacture. That's what I would want to. So I kind of like reduce the number of parts in the mechanism to as low as I can. So it's just literally 2 motors, a motor controller, a servo controller, and a Raspberry Pi, and normal batteries around it as well. So I would like your inputs on this design, and I would like to know if anyone can reach out to me. I'll just share my email so that if someone can help me out with the fabrication or how to bring it to fruition, that would be really awesome. And that's about it for me.
Okay, so you said you posted your contact information in the chat?
Yeah, I'm just going to do that. Just give me a second.
Okay. Okay. Anybody have any questions or thoughts? And
I was just going to say
how big is this
big.
thing?
Yeah, it looks like it's kind of big. So I was suggesting that you break it into pieces so that you can print them individually and then connect them together, at least for the prototype.
I see.
Yeah. What's the diameter of the thing that you were showing us?
So I tend to think in Indian units as in centimeters. So this is 30 centimeters, the diameter of it. So it's about 30 centimeters by around like 7 centimeters height altogether. Okay. And yeah, that's roughly the size of the outer cylinder.
Okay. Yeah. So it's actually pretty good size. So it sounds like something kind of maybe about like that.
Yeah. Yeah.
Yeah. So maybe something a little more compact, but I guess it depends on how many pills you need to accommodate, though. I mean, different kinds of pills.
Yeah. So the good thing about that is like I can actually decide how many of the pill boxes need to be spread around in the radius based on how many pills you can feed into it and all. And like I just did a rough calculation based on like the size of the pills and all, which my parents use. And I found out like having 8 or 9 compartments is good enough for now.
We lost you there. Lost audio for you for some reason.
Oh, am I still audible?
Huh.
Am I still audible?
Yes.
I can hear you.
That's kind of weird.
Yeah, I can hear you.
You're not muted. I don't know why we're not hearing you.
There was a dropout for me in Dallas, at least.
Awesome. So yeah. So basically I did a like size comparison with like normal tablets, like you have paracetamol and like basic tablets that my parents take, for example, the diabetes pills and all that. And I kind of found out that like 8 or 9 boxes is good enough. For like a normal person, I'm not saying for a person with a lot of like diseases and you need to take like 40 pills or something. At that point, I think you need to get a nurse. But yeah, so in that sense, the harder challenge I feel in terms of a robotic problem is the manipulation. Like you need to be able to pick exactly 1 pill and not like the number of pills should not get wrong, right? If you're trying to pick it up. That's one of the challenges that I found because the size and shape of the pills might vary. So if you look into like hopper systems or systems that feed a single part, like a bolt or something in the industry, like the feeder systems, they tend to have a problem with feeding the exactly single part, for example. And that's why I went for a suction gripper. And I think this design works, at least like for the very basic ones that I've seen, like normal capsules. But I'm yet to encounter a pill that cannot be picked up by a suction gripper at this point. So those are like parts where like experienced roboticists might be able to give me some ideas on how it would work or all of that. So that's about it. I just shared my email and my phone number so you guys can reach me out by text or I just drop a message because I wouldn't be knowing most of you. So, and then I'll reach out to you. Awesome. I think I got an email from Mark. Thank you, Mark. Be reaching out to you guys in a while, I guess. Glad to be here.
Yeah, boy. So it sounds like our host has lost audio.
I could try leaving and joining, or the host could try leaving and joining.
Yeah, Steve, can you hear me?
Yeah, apparently not. He can't hear anybody anymore.
Okay. Well, I'll just jump in. Don't know exactly what he's got planned, but anybody else who would like to share something? Yeah, a little strange. Yep, I can see Steve frantically working over there trying to figure out what's going on.
Steve, can you hear us here from Dallas?
Yeah, I'm guessing that the problem's on his end. He can't hear anybody.
Yeah, it seems to be.
You know, signing?
Chat. That's what the chat's for, right?
Oh, right.
Well, tell you what here. Let's give him a couple more minutes, and we're almost to break.
My computer shows he's working now.
Well, we can hear him. I don't know if he can hear us.
He's not giving any indication he can hear us.
Is anyone needing a bunch of circuit boards with components on them they want to scavenge parts from?
I guess that depends on the parts.
Lots of power supply FETs and transistors, mostly.
No. That's what I'm trying to figure out what your backdrop is there, Richard. I mean, it looks like a server rack, but from this view, it seems excessively large.
Is it a hard drive array?
Yeah, I kind of accidentally won an auction. I did not mean to win this auction. I put a laughably low price on it, and then I had to drive to Everett and pick it up.
Well, it looks
if anyone
like
needs
for quite a bit now.
If anyone needs 3 14 drive fiber channel enclosures and the controller, I have 25U of hard drive enclosures sitting in my garage right now.
Does it come with the sandwich eating child?
So, right? Stuff them in there.
I love how the flow algorithm is making him disappear back into the thing and then come back out. That's really cool.
His shirt matches the wall color really well.
By the way, if anybody ever comes across a really good tutorial on how exactly the flow algorithm works, I've been looking for a good one. I haven't found one yet. I found some very basic stuff on it, but not enough that I could really implement it or understand it completely, and that's something I would love to understand.
Hi there. I'm back. It looks like it was my extended monitor just sort of wigged out. Go figure, right?
Oh, we hear you now, Steve.
Yes.
Can you hear us okay?
Yeah, I can hear you guys now. Yeah, it's just, you know, it's just one of these, it kind of looks like a tablet, but it's just an HDMI monitor, you know, so it's, and actually earlier in the meeting, there was a kind of a almost like a flash or something. And then it was fine, but then just a little bit ago, this happened. So go figure, right?
Is it HDMI?
Let me see here. I wanted to share with you guys a couple of things here. Let me get to my, all right, let's see. Okay, share, desktop. Okay, is everybody seeing seeing Google Photos there and seeing some pictures? The this is what my niece's son is playing with one of my little Mechamons here, a little four-legged spider type robot. And you know, he and his brother love these things, but you can do battles and other things with them. They thought that was pretty cool. This is a little guy. He's 4. Actually, I think he's almost 5 now, but he's a neighbor across the street, and he was having a pretty good time playing around with one of these little guys too. And it's amazing how easy these things are for little ones to play with. And that the vacuum back to this, one of those Shark vacuums that's self-emptying. So it's got the vacuum base, and then it has the video camera on top of it, so it maps your house, and then it can figure out where it is. That's pretty cool. This is totally non-robot related, but if anybody is interested in a fiberglass canoe, reach out to me. Don't use it anymore, but and so I'll be happy to, you know. Just got to come and get it. Better way.
Oh.
Yeah.
Dude, I wish I wasn't in San Diego.
I know. Well, you know, I could probably, you know, maybe I could carry it on the plane or something. I also have, this is one of my sons has this, it's a camp stove oven. It's a propane stove and oven. That's the sort of thing that anybody would be interested in. Again, just reach out to me. Be happy to try to answer some questions for you about it. He doesn't use it, but as far as I understand, it works. So, anyway, back to robotics. So, this was serendipitous. So my wife and I went to a park, and these guys pull up. This guy pulls up in this beautiful brand new pickup truck with this interesting machine in the bed, and apparently it's for cutting grass on steep hillsides. You know, because as you can imagine, if you are on that hillside sitting on a riding mower or a push, or trying to run a push mower up it, you know, you can imagine it to be pretty challenging. And so this little thing, it's got you know, 4-wheel drive. You can see that the 4 wheels allow it to translate in its movement, so it can go anywhere. It's being remotely controlled. It's as far as I know, it's not autonomous in any way, but it is remote control. And I'll show you a picture of that. It has a winch that can be used, so you can. It's on the opposite side of what you're looking at here. So he demoed that for some guys from the Park Service that takes care of the grass cutting in these places. But you can take that winch, you can hook it up to, let's say, a tree or a vehicle sitting up on top of the hillside, and then the robot can keep its position or pull itself up the hill or whatever. And I think he said it can go up to about a 50-degree angled slope pretty comfortably. So let me, let's see here. There's another kind of a little picture of the actual unit. While he was demoing this thing, I noticed it looked wet. Well, it turns out that it sprung some kind of a leak somewhere. And so it was spraying itself with, I'm not sure if it was hydraulic fluid. I don't think it was engine oil. I think it was hydraulic fluid or something. But anyway, so he peels the covers off of this thing, and then they're kind of starting it up and running it around and trying to figure out where the leak is. And apparently it's something that kind of happens from time to time with these. Down in the lower left corner, you can see the winch down there. And it actually was very cool that he took the covers off, because, you know, I'm looking at this thing going, wow, what does it look like underneath those covers? You know, and the next thing I know, they're peeling the covers off. You know, I mean, how cool is that? Let's see here. Go to the, there's another shot. I was inclined to stand back a little bit further when they were firing it up, because just, you know, the way the thing was spraying itself, it's like, well, somebody's going to get a face full of oil, you know, off of this thing. The guy looked it up online. Prices for these things are about $40,000. So it's not an inexpensive piece of hardware, but pretty cool. This is what the remote control for it looks like. So you can see you've got, looks like you have the ability to move, you know, forward, backward, left, and right. You can also rotate, so it can spin itself around on a center axis. Translate, so it can steer the wheels in whatever direction, and there's all kinds of, not even certain what all those buttons around the stop button do there, but different modes. And so anyway, it was a kind of a fun diversion, you know, I mean, my wife and I, we were just kind of out for a drive and lunch at a nice local little park, and this cool machine shows up, you know. I mean, it's, hey, oh, you can kind of see on the tires there, you can see some of the oil. There was, you know, you could see it was wet all over the place inside, but yet when he would start it up, there was no sign of oil leaking from anywhere. So it was kind of strange. It was almost like it healed itself, but I'm guessing it didn't really do that. Because machines, you know, if it leaks, there's a good reason for it. And
I love these situations where somebody else's robot is having trouble, and it's everything you can do to control yourself from wanting to dig in and fix it. Right? Tell me you didn't want to do that.
Oh, it was tempting. You know, I mean, I was asking them questions about it, but trying not to, you know, the guy was there to do this demonstration for these park service workers, you know. So, I mean, I didn't want to sort of get into the middle of that, but at the same time, it's like, oh, this is just a really cool machine. Tell me more, you know. I did ask some of them, though. I said, well, how do you guys normally cut this grass, you know? And they were talking about things like, you know, you take a push mower and you tie a rope to it, and you stand at the top of the hill and you lower the thing down and you pull it up, and you lower it down and you pull it up, and it's like, yikes, you know, that was a pretty good sized hillside there altogether. So that'd be a lot of work to do that. And getting around, because of the trees and things, you know, you wouldn't be able to stand up at the very top of the hill because the tree is going to be in the way. So you're going to end up having to go around to the hillside of the tree to get down there. And, you know, not a pleasant proposition. So I'm not sure, you know, if these guys were, maybe their boss said, hey, go check this thing out and give me some feedback on it. Tell me whether we should try to see if we can get something like this. So I'm guessing that was kind of their job, since they're the ones that look like they were the ones that actually did the hands-on maintenance work. So the landscape maintenance work. So therefore, they were probably good guys to evaluate this thing, see how well it worked. One more thing.
Stop and say hi.
I am sorry, Richard. I reached out to the wrong email address for you. I realized that we went practically right by your place. So I told my wife we got to go out there again, and we're going to hit Richard's place next time. And I know you got a charger there, so I mean, like, oh man. So my wife and I did a 670-mile Olympic Peninsula loop 5-day tour type of thing. So we spent 4 nights out there. We went up to Hurricane Ridge, which is what's in the picture here, and did this with a Nissan Leaf. So this is a 5,200 foot elevation up here to Hurricane Ridge, and 5,242 exactly. And I was going to show you the cool thing. Electric cars have the regenerative braking, so I want to show you this. So you see that note the time on this is 1:03 p.m. and the battery charge is at 76%. You see it says it's at Hurricane Ridge, 141 miles. The trip distance is 20 miles. So we were at 0 when we left Port Angeles, about 20 miles up to Hurricane Ridge. And then this was at the other end of the trip. So here it is, half an hour later. We're at 83% battery. So remember, we were down here at 76. Now we're at 83%, a range of 98 miles. And we've gone, let's see if I can get that stuff out of the bottom, out of the way there. If I can get my mouse out of the way. 36.9 miles. So on the round trip coming back down again, we gained 7% of the battery. And let's see, what did I say? It was 141. So was that 50, 57? Yeah, gained 57 miles. So was kind of cool. Had not experienced that before, because climbing mountains with electric cars can be a little anxiety producing, since you don't want to run out, but at the same time, because they can recover the energy coming back down again, you don't have to sweat so much that you're actually using a lot of power to get up the hill, because your car will actually get a lot of that back on the way back down. So anyway, that was very cool. And then the last thing was attended a SEVA meeting, the Seattle Electric Vehicle Association meeting, and ran into Randy Carter there, who I see is online with us this morning. And so that was kind of fun. And I was, in particular, one of the things that impressed me was this Scion here, which is a complete conversion. This guy it was explaining all the, everything. He took an original gas-powered Scion, turned it into an EV, and custom everything in this thing, and it was pretty cool. So anyway, that's all I have.
For Hurricane Ridge, so the percentage looks like it was 76 at the top of the mountain, and then you gained 7% coming down. Yes, that's right. It went from 76 at the top to 83 back down at Port Angeles at the bottom of the hill. So when you started at the bottom, so how much did you lose on the round trip, bottom, top, bottom? Okay. At the bottom of the hill, it started at 96. So it was 96 at the bottom, 76 at the top. So the car can normally do about 2 miles per percent normally on flat travel. So it only did 1 mile per percent climbing up to Hurricane Ridge. But it gained so much coming back down. And I did some math on this thing to figure it out. And regenerative braking is not 100% efficient. It's not even close. But it's pretty significant, because no gas car can do this. Except maybe a hybrid. But it's really cool that electric cars can do stuff like this. Well, if you said 96 to 83 round trip, so that'd be 13% for 40 miles. Yep. So I actually got 3 miles per percent round trip. Huh. So it was even yeah. It was pretty crazy. But I love electric cars. I have 2 gas vehicles. I'd love to jettison them, but not yet. But so
that's the basis of all of these, like pump hydro storage, and there's people who are using a railroad that goes up a hill, and they're taking heavily laden cars and pulling them up a hill. Yep. And then there's that gravity outfit that's taking cement blocks and stacking them or unstacking them. Yeah. To try to store. Switzerland has one of those big giant trucks that brings rocks down from the top of the mountain. So the thing drives itself up the mountain on battery, and then it collects energy coming back down again. And it's like they all just charge it up once at the bottom, and then it's able to recapture everything it needs to get back up again. And right. Yeah. So you don't have to charge it after that, because it just keeps recharging itself from the weight that it's pulling down. Yeah. It's pretty amazing, potential energy. It's awesome.
Yeah. Did Brian mention that was his second iteration of that vehicle?
He might have.
Yeah, because the first one he built got wrecked.
Did it? Oh, okay. I don't think I heard that story.
And then the insurance company totaled it, and so he ripped the guts out of it, put it in the next one.
So somebody sitting behind me said, when I introduced myself and said I drove a Nissan Leaf, and they said, well, you know, if you ever get in a wreck and your car gets totaled, give me a call because I'll buy your battery.
Well, he has a whole company over on Bainbridge Island, I think it is.
Yeah.
And that's what they do, is they build EVs. And he mentioned at the meeting that he's took the 24 kilowatt hour pack out of a 2011, which is the first generation Leaf, and slapped in a 62 kilowatt hour pack, which gives him 6 times more range.
Yeah. Yeah. In fact, I understand the efficiency of the older Leafs is so good that you actually you go further with those than you do with the new ones with that same battery in them.
Yeah, well, they sold me my current Leaf on the promise that it was more efficient than the previous one.
Wow. We are at 11. I would like to take a break, and we will get our presenter going here in a bit. In the meantime, I'm going to go ahead and just throw a slide up here with a countdown timer on it. And let me see here, where's the, and then we will, okay. Y'all seeing that?
Yep, looks good.
Okay.
Very nice.
So let's kind of resume here, you know, kind of 11, or, you know, maybe 11, 10, 11, 12, something like that. So go ahead and, you know, do what you got to do here over the next few minutes, and then we'll get Josh going.
Hey, Steve. Oh, second Tuesday every month. Good bad question.
Hey, Greg, if you have a second, there was a question about what board house you used to make those very lovely printed circuit boards.
JLC PCB.
They seem to be quite popular these days.
Yes.
Is that a laser pointer that's making those numbers in the countdown clock? Looks like it's got that laser sparkle to it. I bought myself a projector, a video projector some time ago that used lasers. And the reason why I bought it was because the idea was that you would never have to focus it. It would always stay perfectly in focus, irrespective of how far away the screen was. And it did, you know, but I couldn't use it, I couldn't stand it because that laser sparkle effect was in every one of the was in every one of the anything that it projected. It would have this like vibration or sparkle to it on the screen, and it bugged me. I couldn't deal with it.
Yeah, that would drive me nuts too.
I was actually hoping to do a heads-up display, turn the brightness all the way down, and then mount it on a hat or something, and use it to project an image via a half-silvered mirror in my eye. And I found out two things. First off, you couldn't turn it down far enough, and I couldn't get half-silvered mirrors that were silvered low enough for reasonable prices. And even if I could done of all of that, then the sparkle effect still would have driven me crazy, so I gave up on it.
Yeah.
Still wish I could build a head-mounted display. I've always wanted one of those. I was sad that Google Glass went away.
All right. So let me close that. And so we should just be back to normal video display here. And we'll get our presenter going. So we're very pleased to have Josh Pieper share with us there from Boston, Massachusetts. He is, let's see, he's been building robots professionally since 2004. He's done stuff in marine systems, wheeled ground vehicles, in off-road and on-road applications, and he's now into legged robots. And as a hobbyist, he's competed in many enthusiast events like Sparkvun, ABC, Robo Games, Robo Magellan, and Mech Warfare. And he enjoys all aspects of machine design, from software to mechanical and electrical. And so with that, I will turn it over to Josh. Thank you, Josh.
Thank you, Steve, and thank you for having me. Hopefully when you mute, your echo will go away. So I'm happy to answer questions at any point. Just put them in the chat, and at the end of each slide, I'll go through and chat people up, and we can unmute if we need to as we go through. My presentation is kind of lightly annotated YouTube videos documenting first who I am, then documenting the conception process for the Quad A1, and then at the end, a little bit of shilling for mjbots because I'm a presenter and have a business. But it's largely all stuff that's in the robot, so hopefully it'll be interesting to people here. This is me. Steve already introduced me. I got my professional start building autonomous underwater vehicles at Bluefin Robotics. Those are marine systems. People were mentioning earlier that high voltage and water don't mix, and I can test that is definitely true, especially when you have salt water as well. It's even worse. And fortunately, the software side of these systems was fun, but not like terribly hard, because robots just assume the entire ocean is free and you can go anywhere you want to. And if you hit something, boy, you got unlucky. But a lot of the work was maintaining fault tolerance and dealing with the fact that you have high voltage electricity and corrosive salt water and making the machines continue to work. Switch on. So after that, I started a company called J-Bridge Robotics, or co-founded it. We did automation for off-road industrial vehicles like.
Everybody else lacked their meeting controls as well, because
Carl, I had to exit my browser and start over again. And when I came back in, I had no audio, so I had to do that again. And then the second time I came back in, the stars were aligned, and I'm.
Okay, well, I'm going to jump out and in again. I'm trying to use the Zoom client itself on Windows 10, and it's just not behaving right. So.
Yeah.
Okay, I'll be back in a minute.
Well, let's just blame this on Zoom, man. Okay.
You should.
Everybody's good with that?
Steve, I don't think it's anything you did. It was too coincidental that Zoom wanted to update, and.
Oh, do you think that Zoom pushed an update in the middle of the meeting and it?
They did in my case. They forced it on me, and now it's behaving like crap. So.
Oh, jeez.
I'll be back in a minute.
Too.
Okay. Well, let's. All right. Let's see. How's Carl? I see Carl up, but he's not. No. Well, of course, you don't need video if you can hear us. So.
I can hear you and see you, but I can't control the. I don't see the pain of all the viewers, and I can't turn off my video or audio.
Wow.
Those buttons are not present. All I see is the screen that shows the meeting. So I'm oh wait, where did it?
That is weird.
Oh, there it is. It's just hiding in another place.
Okay.
They had one of those pop behind to invisibility windows.
Oh, love those.
Yeah.
Well,
okay.
Is Josh still here?
Yes, he is.
I am still here. I came back.
Well, Josh, I already introduced you, and so I'm going to take my hands off of everything here because I don't know what happened. But please continue.
Okay, let me get the chat up again, and I guess people can rejoin or watch the recording when it comes online, if for the parts they missed.
Yes.
Let me try to share my screen again. Which one do I want? This one, perhaps. So can everyone see my screen share again? Yes. And
Yep.
great. And were you able to see the videos I was playing before? People who were on?
Yes.
At Zoom frame rates at least? All right. So.
See anything.
No one. Well, I will continue. If you have, at least as someone can see it, I'll call it good enough here. And I'll leave the rest for recording.
Oh, let me jump in for just a second. If anybody doesn't have their mic muted, I will follow suit and do the same thing. So please mute your mics.
Great. So back to where I've worked. JBridge Robotics, we developed automation for off-road industrial vehicles. This is a video showing a quarry automation system we developed, which would let one vehicle record a path, and then you could have any number of vehicles follow it, which is common in a quarrying situation. There'll be like 2, 3, 4, 5 trucks all doing the same thing all day long, going from where they're blasting the rock to the crusher where they crush it. We also developed a system for agriculture and tractors that could automate harvesting and planting. The coolest part for me when random people would drive by and see our systems operating here. This is just a random YouTube video from some passerby who saw our tractor driving along with no one in it and was like, what the heck is this? And it's just going around doing its thing. And that was some of the coolest part about professional robots, is getting to see things work, because this would just go all day long, going back and forth between collecting grain from a combine and taking it back to the semi-truck all day long. And all these, I don't know if Steve has a place for them. These are just all YouTube video, public YouTube videos. And so eventually, if you want to see the whole thing, you can switch to those. We took JBridge, both ag and mining, had a really rough stretch. So we kind of sold the company to Toyota Research Institute, and I worked there for a while on their self-driving car program. This is some semi-marketing speak covering the platform there. I mostly worked on their software systems, developing the infrastructure that recorded gigabytes per second of data from many sensors and let all the researchers analyze that and make sense of it to develop new algorithms. Let me switch on here. I've done a lot of hobby work as well. A friend and I from JBridge, we entered in a number of robo games competitions. This is Robo Magellan, which is founded at SRS long ago. Thank you SRS for that. We did this just for fun at Robo Games in San Francisco. Of the 3 years we entered, we won 2 of them, and one we had a machine destroy itself. But it was a lot of, doing those competitions is a lot of fun. Here this is just an off-road RC car with, this version has an Odroid. The first year we did it, we just strapped a laptop on top. It was the same basic software. But it could go pretty, when it was running well, it could go pretty fast, like 12 miles an hour, and it used vision to identify the cones, and it didn't use vision for anything else aside from seeing the cones in the Robo Magellan. It just used a relatively accurate WASP-capable GPS, which was enough to drive through the narrow spots in the San Francisco course. This video was our winning run in 2015, where they perhaps, expecting no one would hit it, put this cone way out in the back, which they denoted as a 0.001 time bonus cone, which they assumed no one would manage to hit. Which we got it, which then made our official time be like 2 seconds to the run, which made it the fastest timed run in their history, but not because it was particularly fast, just because we hit this hard to find cone. A similar version of the car also ran in the Sparkvun autonomous vehicle competition for a few years. In that event, you just go around a track. The years we did it, they had various obstacles or bonuses you could hit. This year, there were barrels you had to avoid, a hoop you could go through, and a ramp you could jump. And this version was maybe a slightly older version that had a mini ITX computer inside an aluminum case. But it used cameras to avoid the barrels and to go through the hoop and to jump over a ramp as it was going through the course. I think we got second place one year in this event. The rules weren't as forgiving. They were very biased towards consistency, and ours were high performance, but not necessarily the most reliable. So we would get like 2 runs that would work and 1 run that would explode for some reason. But I'll let this one run until it hits the ramp, because this event had this ramp which was very perilous, because you'd either hit it all the way or you'd miss it, and if you get it part way, usually your robot would crash. And so here we used a camera to find it so it could take the ramp and go over. Let me skip ahead then. For some reason, all my slides lost. Oh, that's what happened. Well, anyway, the text is missing on all my slides. I started at approximately the same time frame doing some work on legged machines. This is just equivalent of a Dynamixel style servo. This was using Herculex hobby servos, but smart ones. This used a TTL level bus. All the servos were on a bus and had a gate engine to allow it to walk somewhat. I took that, so we took that system, this was the same friend and I, and we put a inertially stable gimbalized airsoft turret on top of it and entered it in the Mech Warfare competition, which that competition has you get to FPV, so teleoperate the machines and fire against detector targets on other robots. This was a lot of fun. Once again, our machine was very high. When it worked really well because we could shoot while moving, which no other machines could do. The downside was that it used USB and all kinds of other stuff, so occasionally it would flake out and just die. This was a run where it won because it was able to shoot while it was walking around because of the stabilized camera and video. So that's a little bit of my background. Now I'm going to go into the story of this Quad A1's development, and I started from that hobby servo machine back in 2013 and wanted to make something that was more capable of doing dynamic maneuvers. But there is, of course, a lot to do from going with off-the-shelf hobby servos to a machine that can run fast over open ground. For the purposes of this presentation, I broke it up into 3 semi-discrete thrusts, although in practice, when I was doing it, it was all kind of intermingled craziness, as you imagine if you have a complex project where lots of things were happening. But one was doing motor control using field-oriented control to control brushless motors, which are able to control. Another was building a reducer for those so that you can have higher torque and lower maximum speed, because for the brushless motors in the size class you're looking for, they're still too fast and too low torque for legged machines. And then building a chassis and leg hardware to turn that into a full robot. So I've got some random videos and pictures showing the development in those 3 different domains going towards this overall robot. And I'm actually going to edit my slides live here, which I should probably never do, but because all the text, while we were waiting, I did like a re-template apply, and it put all my text out of the frame. So when I started, I thought I'll just use an off-the-shelf motor controller. This was in like 2017 or so. And so I got a VESC, which is commonly used for longboards. And so on longboards, they just go fast and go for a long time, but it had a servo-based mode, which I thought I could make work. And I built a planetary gear train reducer with off-the-shelf gears and the 3D printed housing, and hooked it up to the VESC and got it working with position control. But the VESC's position control was relatively immature, and I got a few bruises from it doing craziness, especially around like the 0 to 2 pi rotation threshold. It would get confused and like all of a sudden spin multiple revolutions. And also I wanted to make everything permissively licensed open source, and the VESC was not suitable for that. So I decided to make my own motor controller. So I started with a TI gate driver, which is the DRV 8323 is what I used. And I built a very small board based on its reference design and an STM32. This was one of the, this was probably R1s. This is one of the first revisions. And this revision used an RS485 bus. So it's like a smart servo, but for brushless motors. So it would do force control and force feedback, as well as position control. I took that and used basically the same planetary gearbox I had before, built two of them side by side with a parallel linkage leg, kind of looks like a leg, and set it up on a linear rail and made it jump. And this was the first day I got that leg to jump by putting force down and going up in the air. So this was a proof of concept that yes, I could make force, apply it through trajectory, make something jump off the ground so it has a fair amount of force and is able to make that work. It wasn't terribly practical for a number of reasons. One was that the leg geometry was not super suitable for a whole robot because the parallel linkage takes up a lot of space, at least especially that geometry of parallel linkage takes up a lot of space. So I next iterated and designed an entire new leg with the similar geometry to what we used on that servo-driven robot, except this time the knee joint is driven by a belt, and there are two motors that face in towards each other. One drives the upper leg and one drives the belt, which then makes the knee go. And that way there's really no motors on the moving parts of the leg, which reduces the inertia a lot, which lets it be more dynamic. And so that was the first video showing that working. I'll skip on to the next. And so I took that and said, I'm going to push forward and make a whole robot based on it. So I built 3 legs, stuck a yaw joint on, put it on a chassis, and built it together and crossed my fingers. And when you, minimal math saying maybe it's feasible. And of course, the answer was no, it's not super feasible. While there is nominally enough torque for that to work, the overall bandwidth of the control was not really sufficient, especially the joints which I expected least, the shoulder joints, which nominally need 0 torque when you're standing. It takes actually a lot of torque to restore from when you have disturbances in the yaw axis. And that made the machine relatively incapable of standing up, much less walking. This is just a video showing how wiggly it was in the yaw domain. And if you tip it sideways, there just wasn't enough restorative force to be able to keep it going up. The motors can put out a lot of torque, but yeah, see there, it tipped over all the way. But the disturbances were too much and it wasn't able to work. So about the same time as this is when the Mini Cheetah by Ben Katz was released, and I decided to somewhat steal his idea of putting a planetary gearbox inside the stator of a brushless motor. The problem I had with my planetary gearbox before is it was too big to make for an actual usable leg. But by putting the planetary gearbox inside the stator, it makes the whole motor assembly not much bigger than the motor was originally. You still need a little bit of extra stuff for the housing and for the controller, but with that approach, it would let me get a 6 to 10x reduction what you can do with planetary gears, which would make the whole machine more feasible. So I designed that. We saw the cat blowout. I did an initial fit check 3D printing, but in order to do a frameless motor design, the rotor and the stator have to be aligned within about 0.005 of an inch to not crash into each other, which you can't really do in plastic. Even engineering plastics flex too much to make that happen, so you have to use metal. For my first design, I made the smallest number of pieces machined which were 3 of the pieces of the 7-piece assembly were machined in aluminum. And so I designed those and sent them off to a job shop and hoped for the best. And actually 2 of the 3 worked on the first time, and the other one only needed 1 revision, which was for my first machining design was, I consider, a pretty good success. This is a picture showing all the parts for one of the servos in the Quad A0, which I took an existing off-the-shelf 8108 brushless motor and used a mill to disassemble it and rip it apart and then reassemble it around these parts. And so those are all the parts that went into one of the servos on the original Quad A0. So there is the stator and the rotor here, the 3 aluminum machine pieces, some off-the-shelf gears, a ring gear, which I had to post-machine on a lathe, some bearings, the controller, and a whole bunch, some 3D printed parts, and a whole bunch of inserts and screws. And so that's what went into one of the servos on the Quad A0. I went too far forward. And then these are just some pictures showing the assembly process, starting from putting the gear in to putting that external 3D printed housing on and putting the stator in. And this got me closer, but not there. This machine was able to walk, kind of. Having this machine had those servos for 4 joints that controlled the abduction on each of the legs, and still had direct drive for the upper and lower leg. And here's a video showing it walk. It was able to move, but once I added the weight of all those bearings and crap on the servos, the direct drives were no longer sufficient to allow for reliable control. So iteration again is building enough servos for every joint, which I buckled down. At this point, I was trying to enter this as a forcing function into a Mech Warfare event, and I had about a month left. So I spent 3 weeks working like 90 hours a week building servos, because each one of these took like 3 man-days of effort to build at each one. And so I built 8 more plus a spare 2 servos and designed a new leg based around those servos, which has the 2 servos facing inward, so the same basic design, but with the gear reducers. And this was able to walk more reliably. It was able to walk for a couple hours at a time without braking, which was better than anything I had before. Still wasn't very good, but it worked. It worked better when it didn't have the gimbal stabilized turret on top, which added an extra kilo or 2 to the weight. And so this was a demo video that I took for Mech Warfare where I walked around for 30 minutes slowly, but it did walk for 30 minutes, standing under its own power, and was able to shoot some airsoft BBs around. That said, it's still, you can look at that video and tell that it's not running. It's actually probably slower to move than any of the hobby servo machines that were out there, but it had promise. And so I did yet another iteration. But before that, I'll switch gears and talk about all the other things that had to happen beside the motor to make this robot work, which there is, of course, more. So there are a number of other boards that I built and designed and wrote the firmware for. One was this Pi 3 hat, which is a Raspberry Pi hat that has 5 CAN FD ports on it, power conversion down so it can run from the battery bus voltage, and the inertial measurement unit, which runs an onboard Kalman filter to provide an attitude solution. It also has a 24LO1 receiver, which for things like robo games is useful because the Wi-Fi environment is absolutely terrible there and you can't really use Wi-Fi effectively. But I don't actually use that very much anymore because there haven't been any events in 2 years where the Wi-Fi environment is terrible. But crossing fingers, someday there'll be events again. So that connects via all the SPI buses on the Raspberry Pi and lets the Raspberry Pi command and control all the servos as well as having an IMU. Also, I've got this power distribution board, once you have 12 servos attached to a battery, plugging in, there's a lot of capacitance on the bus. And so if you just plug it in, you'll get a big spark, which the inductive spike on that can overvoltage everything on the bus. So this does pre-charging effectively and also monitors the power on the bus, so the robot can tell how much power it's using. And it has a soft switch, so it can turn itself off more slowly. So those are the other circuits. However, as you saw, that quad A0 still barely walked, and when it took it to Robo Games, it actually broke after like an hour of walking around because the 3D printed parts just consumed themselves under the load, which was not too unexpected, but it happened. So yeah, and this was a very long, and I started with that hobby servo in 2013, and it's 2022 now. So this has been a long process with many steps. But to move on to the quad A0, I redesigned the servo to not have 3D printed parts in it, or at least basically no 3D printed parts, both to make it be more reliable and to reduce the weight. To make the parts that I have 3D printed had to be extremely bulky to last even as long as they did, which made the motors and the whole robot be pretty chunky. And that gearbox, as I mentioned, took like 3 man days per gearbox to assemble and build, which was an unreasonable amount of effort if you wanted to make more than one of these. It's like nearly a month of full-time effort to make one robot. So I designed a new version here, which this is just another CAD explosion, which has mostly machine parts and only takes an hour or two to assemble from individual pieces, which makes it more feasible to build a robot. It's like a day or two to build a robot's worth of servos instead of a month. So Bob asked what kind of material did I use for the 3D printed parts, and basically everything that I've 3D printed that you see here has all been in PETG, all on a Prusa Mark IIISs. Mostly because everything is mechanical, it's all surviving loads, and in many cases it's also potentially hot. And the PETG has been it's super easy to print on a Prusa and gives excellent results. And with the Prusas, I have multiple Prusas with more than 400 days of print time on them, and they have one failure a month or something. So it's super reliable, no-brainer. Thanks to that question, Bob. So that was the CAD explosion from my QDD 100. For this version, I took one of those detours that we often do where I wanted to get more familiar with how to manufacture it. And so instead of and I also wanted to be able to iterate more quickly rather than sending things out to job shops. So I got a desktop 5-axis mill, spent a lot of time on YouTube watching CNC machining videos, and machined multiple iterations of all the parts for this on the Pocket NC. It was very instructive. I'm glad I learned it. It took a lot of time, especially this desktop mill, as you can see, is not particularly a VMC or anything, so it's not fast. It goes pretty slow. And so the machining time for one servo's worth of parts was like a week or something or more. So the assembly time was fast. If I did everything on the Pocket NC to machine it all, it would be not slow. But for prototyping, it's not infeasible because it's okay to take a week to machine one servo's worth of prototypes, especially sending out even one part to a job shop that often more than a week of turnaround time. So I'm glad I learned it. It was fun. I built the whole prototype. It's the same video here. Let me switch to the next one. I also redesigned the leg to, instead of having concentrically facing motors, the motors were serial in design. So there is the same abduction joint which swings the whole leg in and out, and there is the upper motor joint actually moves the whole lower motor, and the lower motor joint is rigidly fixed to the upper leg and has a pulley inside to drive the belt. And that has the same, the two motors, there's slightly more inertia because this upper motor is now spinning the whole lower motor. but it's still all relatively concentrated in the shoulder joint, so there's not that much inertia. And it means this leg can now spin basically 360 degrees modulo wiring challenges. James asked if it causes more cantilevering, and yes, it definitely does cause more cantilevering. These servos were designed around that level of loading, so that's possible. So it's workable. There's a bearing in the surface that transfers the load. I think somebody must have unmuted themselves. So if you're unmuted, mute yourself again. But the range of motion was key, and it's also less complex to assemble too. But with this range of motion, in normal walking, you still want at least 180 degrees. In the concentric facing, it's tough to get more than like 100 degrees of motion. And if you want to do fanciness, the 360 degrees is even better. And so putting all those things together, I made a new chassis, which puts it all together. Let me put this, sorry for fixing my slides while I'm presenting, but such is life. And so then the new robot looks like this. It looks more like a robot. It's able to walk more effectively and go in both directions. And with the servos, it's able to hold a decent amount of load. When I took this video, that was the extent of the speed it can move. But that's still even better than the one that I took to Mech Warfare, the Robo games. And it didn't break. The servos were way faster to build. For the production servos, I still had a machine shop build the bulk versions. I didn't do those on the Pocket NC. So in that sense, it didn't actually take that long to build either. But that does not, okay, someone put a question here. You consider one axis. So Carl asked, did you consider moving the one axis more towards the center of the robot so the mass distribution would be better centered around the axis of the shoulder joint? And go back to the video of that leg here, or the picture of the leg. And for this leg geometry, the constraint on where this motor is actually where the leg will intersect with the chassis. And so the leg is pushed out far enough so that the leg can swing all the way up without hitting the side of the robot. And so it's just far enough so the leg won't hit the side, which allows it full range of motion. It would be better to have the motors further in, but in this case, it was constrained by the chassis design to continue letting the legs have full range of motion. I could make the leg really long, but it's easier to make this part, the shoulder joint, bulky than to make this part stick out extra far as the bolts, the bellies and the bolts go.
I think, I guess what I'm asking is that, like, if the body of the chassis was wider, so then, I don't know the names of those two joints, but there's, yes, you got the one on the outside and the one on the inside, then the one to the chassis.
Yep.
Okay, so it seems to me that if, like the one on the chassis, that comes off to the inner motor, not the outer motor. So I was wondering if that axis on the chassis one, if you just shifted the chassis motors out towards, made the chassis wider, then the axis coming out of the chassis could go down the middle between the other two motors. And then it would give you a chance of having the mass better centered over the leg.
Yep. The challenge here is for this 3D printed plate that the motor mounts onto, there's a fixed amount of margin that's needed in addition to this circular motor that has to be laterally. And the leg, when it swings up in this geometry, this leg just clears the chassis through all positions and orientations.
Oh, okay. Now I see what you're saying.
If the motor is slid out, then the chassis slides out, which means the leg would interfere with the chassis when it swings back.
Because the elbow. Okay, I got it. Thanks. Now I see.
So this is, it would be better if it were further in. And to make it further in, I have to redesign this plate to require less lateral tolerance around the chassis, which I'm actually kind of working on doing. But it's, in this case, it's not a terrible, that inertia is not really a big limitation on the performance because there's plenty of torque in this motor to handle that. And that joint, the inertia doesn't matter that much because that joint doesn't really rotate that quickly even when you're running. So it's that's not a super big issue. And then James asked, a gear train to offset the shoulder drive motor from the leg would allow the motors to be a lot closer to the axis, but solving a problem that doesn't cause problems is a waste. And yeah, so this was intended, design was supposed to be relatively simple, and it works, this part at least works. So from the software perspective, I had a simulator that we had made for our little hobby robot in 2013, and it was based on Dart, which is a dynamics toolkit out of university. And I revamped or resurrected that. It's like 500 lines of code, but it runs in lockstep with our actual robot software on a desktop machine, so you can test out things on the computer, which is, it's not super realistic, but it's accurate enough to check many types of situations and at least see if the torques and powers are sufficient to execute a maneuver. I haven't invested a lot of time in making it be realistic, so it can do, like there it's hopping, that the robot can actually do. In the simulation, I've got it to do a backflip, although it can't do that in real life. I invested a lot of effort in making a telemetry and replay system, which captures all the data the robot records from the joints, as well as from the IMU at the full rate. The robot runs its control loop at 400 Hertz, which results in a fair amount of data being recorded. That all gets stored in real time on a Raspberry Pi, which you can then look at after the fact, synchronized with video and a 3D replay of where the foot positions are in time. And you can also plot any arbitrary values in a 2D time domain and then play that forward or backwards or step in time steps, which lets you actually make progress on the things you want to do, which is make the gates better. So in that first video was still, that you saw, the most recent video you saw of it walking was still using the same basic technique we used for the hobby servo robot, which let it go maybe a half meter a second max. So I got questions of what simulation software was that? It wasn't Drake. Drake was actually used or developed at TRI where I worked for Toyota, but that simulation software was Dart, which is D-A-R-T, which is, it's much older, but it worked. The Raspberry Pi recorder and visualizer, the recording happened on the Raspberry Pi, the visualization has to run on it. It's not even set up to compile on a Raspberry Pi, it just runs on a desktop Linux machine. Bob also asked, do you use encoders on the joints? To do field-oriented control, you need to know the exact rotor position, one way or another. For this controller, the Modius controller that I'm using here has a magnetic encoder integrated on the back of it, so it can, at any point in time, exactly determine where the rotor is in the system on each motor. However, there is a gearbox on there, so that introduces an ambiguity about where you start, because it's one full rotation of the motor is 6 times of the rotor. It takes 6 revolutions of the rotor to make 1 revolution of the output. So I just use a fixed turn on position where you have to turn it on and it says, oh, I know I'm within 1/6 of this position, so this must be where it is. And so in that sense, it has absolute encoders on all 12 axes that it uses to measure position and velocity, or rotational velocity. And yes, that is, James, is the correct URL for Dart. Looks like I'm almost out of time, but so I'll go quickly. So I did a lot of work on gates. Here's a view of a smoother trajectory that I worked on that gradually accelerates the leg when it takes off, spins it around, and then gradually decelerates as it comes down. I did some work to make some of the control be done in Cartesian space, which made the compliance more robust, because the compliance was previously done just on a per joint basis, but once it's done on in the Cartesian space, you can make it have a lot less jiggling while being more compliant. So this is a video showing that. Let's skip ahead now. I did a little bit of work to do a simple balancing controller, which is not really a controller, more as it plans when the legs pick up and when they set down to keep the center of mass equally spaced around the center of support, which is only roughly true, but it still allows it to go much faster. And so this is probably walking through a whole bunch of different lateral and translation maneuvers at up to a meter a second. And it doesn't tip around or wobble too much. A lot of what you see in a hobby servo quadruped, if it ever picks its feet up very long, you'll see it tip over side to side because it's not well balanced. And that's one of the advantages of this high control rate machine with the planning, is it's able to keep itself relatively balanced. And certainly it has room for even better results than this. Let's skip on to the next. I set up the IMU and did a lot of 3D geometry so that it could accurately keep its balance even when operating on hills. So this is a video of it walking on like a 7-degree slope. And you can see that as it gets on the hill, it shifts its center of gravity so that it keeps it above the legs, so it maintains that balance even when it's on a hill, which if you've ever seen someone try to take a hobby servo-based machine on a hill, you'll see that the center of mass, if it's tuned well to walk on flat ground, it won't really work at all on hills. Question, is this thing remote controlled or using some path planning ops avoidance algorithm? All the videos I have here are purely teleoperated. There is no onboard autonomy at all. The control you send it is translation and rotational velocity and a body attitude to maintain. And so all this is just piloting with the joystick. And in fact, the Raspberry Pi uses basically all of its processors to do this gate engine. So there's really no room left on the Raspberry Pi to do much of anything sophisticated from an autonomy perspective. Anyway, there you can see it shifting its center balance from the side, which is easier to see. I did 3 different iterations over time of getting it to stand up from the ground so that it could work on more varied terrain. This is the current one where it picks up its legs to get them to clear the ground, then positions them precisely, and then pushes them down. So all that phase is kind of fixed. And then once it gets standing, then it enters the normal gate engine. But that lets it stand up from, it can do up grass, leaves, hills, things like this, which are kind of grippy, like the EVA foam, and so many different types of surfaces it can get stood up from effectively. I made a simple web UI for it, which is what most of this control is done with. You can either do it from a desktop with a gamepad or from a phone with a Bluetooth joystick, and it has like 5 checkboxes and drop downs to change the speed profiles and lets you command the different axes. And then with all those things, I was able to work on trying to get it go faster. And so this probably has one of the fastest speed records for a hobby machine. It can go up to 2.5 meters per second, maybe even a little bit faster, but 2.5 is what I got video for. And so that involved using all those gate improvements that I did, as well as a number of other improvements to get it to be stable and robust as it was going fast. And so this video sequence shows a number of increasing speeds starting at like 0.5 meter per second, which is 1 mile an hour, and going up to 2.5 meters per second, which is a decent jog for a person, 2.5 meters per second. This gate engine is still relatively simplistic, and it doesn't work that well if you have flight periods. And so for even at the fastest time, there's just only a very brief period where all 4 legs are off the ground. The hardware is capable of more than that, but the gate engine can't really handle. It becomes unstable if the feet are off the ground for more than a few milliseconds each step. And so here at 1.8, it's still all roughly on the ground. And at 2, you can maybe start seeing like a very tiny bit where all the feet are off the ground. And then when it gets up to the fastest periods, it's more like 5 milliseconds or something for each step that all the feet are off the ground. But having the ability to record the data and step through video frame by frame and compare it with the readings from the legs and the IMU really made this possible. So here's the high speed run at 2.5 meters per second. And you can see it's a run. It has all the legs off the ground very briefly. And it can do that. It has to be relatively flat to achieve the high speeds. All right, so that is my tour of the Quad A1. Now is my shill time, very briefly because we're over time. So for mjbots.com, I've been selling all the pieces that I've used in developing this Quad A1. You can buy basically everything you need for it from mjbots.com. People have been buying them, most not to build Legged robots, but to build all kinds of things. Some for Legged robots, some for arms, cobots, automation solutions, art displays, just experimenting with hobby things. You can get the Bear controller. So this is the Modius controller. It can turn any brushless motor into a high-performance servo. It's not too it's expensive compared to motor controllers. It's like, or hobby ones, it's like $89, but that's not too bad for a brushless motor controller, which are typically much more expensive. And it gives you, it does a 40 kilohertz control loop. So it has very high performance torque and bandwidth control. And you can do things like the Quad A1 or other projects to that complexity with it. And it's similar in design to the mini Cheetah controller, but it has a lot of enhancements and was developed independently. So it has a higher voltage, higher current, higher bandwidth communication. It has a secondary I2C port, so you can put a second encoder on the output. And it has a GUI that you can use for command and control, which I think I had maybe the video here is the second video. Well, anyway, we'll show it eventually. I also have the QD100, which is the servo that's used in the Quad A1. It has a unique combination of high speed, high torque, and low mass, which it's probably actually the most competitive on all these axes anywhere that you can buy. And it's not, it's expensive for hobby things, but it's under $500 for something that can do 600 RPM, weigh under a half kilo, and still put out 16 Newton meters of torque, which is what the Quad A1 needs, but a lot of other things need that too. And so that's a pretty powerful combination. And it has a Modius controller inside. Here's a demo of me running two of them virtually paired with a Pi 3 hat. And so here you can, I would call it virtual teleoperation. So that's it throwing a 1 pound ball. And so I'm just using one and wiggling it, and the two motors are synced together. So you can move either one, the other one moves. It's like they have a chain connecting them, but it's all just software by wire. And you can do crazy things like that, like arbitrarily change the gear ratio as you go along for other things. Here we have sold a half dozen Quad A1s now, though they're not officially listed for sale, just from people who ask about them. And so it has similar specs to Mini Cheetah. It's not quite as capable, but it's customizable and all open source. I should have mentioned that all the firmware and PCB designs for all these things are all open source under an Apache license. So it's permissive. You can do whatever you want to with it. Granted, that's kind of academic in today's COVID world where you can't buy anything, but when we get back to where you can buy things, it might be more useful. I've got, so this is some glamour video I took for an update in November last year. The Quad A1 can go around on lots of different terrain, grass, gravel, pavement, hills, all those things. And this is with the relatively simple gate algorithm that's running on just a Raspberry Pi 4. And as mentioned before, this is all just teleoperated. Let me switch to the next slide. Both the controller and the servo have dev kits, which aren't too expensive and have everything you need to get started. So that comes with a power supply, a CAN FD converter, and brackets. So you can just plug everything in and in 5 minutes be typing at the GUI, doing force controlled motions or arbitrary trajectories. And so a lot of people really like that. If there's Scientific made a video showing that, so you can see that. This is a video of that UI. There are pure Python libraries for all of these that let you command and control them in Python, as well as you can just make the CAN frames yourself. This diagnostic utility exists. Their GitHub, as I said, everything is Apache open source. And we have a Discord. It seems what all the cool people are using nowadays. So you can get support 24/7, either from me or from other community members. We have lots of people from around the world. We have customers for mjbots from 6 of the 7 continents of the world, only missing Antarctica so far. So there are people from every time zone, and there are a number of published projects. So Stanley is one that, if I could play this video. I have to present, I think. There it goes. So this is I played it and then it, of course, stopped. This is an alternate quadruped design based on a capstan system, which uses Modius controllers, but it uses a capstan reducer, which is much lower cost, but it takes a lot of manpower to assemble. And so here's a demo of it moving very fast. That's real time, so it can spin pretty darn quickly. And so that just has off-the-shelf brushless motors and a bunch of 3D printing and cables design. This Bruce E, he's building a leg based on the Modius controller and brushless motors. Somewhere here is a video of it doing stuff. And so like there's a leg of it, video of it breaking and moving. I made an automated wire stripper, which was, is this gonna play or not? Which shows how fast and precise the brushless motor can be. So that's in real time, cutting and stripping wires, and now it goes into slow motion. So you can see it goes, this is just operating a manual wire stripper programmatically. So it strips one end, cuts the insulation, puts a little bit forward and strips it off, and then you can go back and see it in real time. So I actually build a lot of harnesses anymore, so I use that to cut and strip all the wires for that. There's also another one, and Scientific has done many videos with Modius controllers. And in order to keep this relatively limited, I will call that the end of my presentation. Thank you for humoring my wasn't overly long once you count the disruption in the middle, but.
Oh, that wasn't your fault. So we're happy to give you a little extra time for that. Thank you so much for presenting to us. I'd like to get a copy of your slide deck to post, if that'd be all right.
Yep, can do.
Yeah, you can just, if you want to just share the link. I see you had them on, you've got them on Google Slides, so just send me the shared link. And what I usually like to do is turn it into a PDF and then put the PDF on the website. So.
Yep, it won't be quite as useful with all the YouTube links, but you'll get to see at least one picture from them.
Yeah, and I think it should activate them. So I'll take a look at it and see, and whatever makes sense. Well, thank you so much for joining us, giving us a little piece of your day, and I hope everybody here found the presentation interesting. That's a very, very cool project, and your company has got some really, really fun stuff that it's doing. So glad you could join us.
Yeah, I will hang around afterwards if anyone wants to chat or.
Yeah, any questions here from anybody?
I have a question about the cost of the servo system. I just want to be very clear. I think that the $500 you're charging for that is tremendously fair, given what it does. That's great. But I'm curious if you have any thoughts about reducing the price of that in the future, like what would have to be done in order to get the cost down, or what the major cost points are in that whole system.
To be honest, there is not much that will reduce the cost of this style of design shy of large volumes. The challenge this design requires maybe not quite as many machine parts as the current design has, but it requires at least 4 or 5 CNC machine parts, precision steel gears, precision wound rotors and stators, which even when you get them directly from the factory in China, which is what I'm largely doing now, there's still a lot of cost involved in that. For lower cost, like the capstan drive that Stanley uses is probably the next lowest cost you can get at the expense of requiring a lot of manual assembly and 3D printing time. And his net cost is probably half of what these are per joint, maybe a little bit less than half.
So what we need to do is basically get everybody to buy your servos, and then as the quantities go up, the price will come down.
Yeah, I mean, to some degree that will kind of happen because of all the crazy VC funding that's going into it. Although in practice, it's kind of a vanity project for Chinese big tech companies now, is to have a machine kind of like this. And so they're doing large production runs in the hope that people will buy them. It's not clear to me that there actually is that big of a market for hundreds of thousands of these a year. It'd be nice if there were, but I'm not hedging my bets on it. And so to some degree, this class of actuator will exist, and there'll probably have to be other classes like that capstan-based one for even lower cost solutions that come with alternate trade-offs, like increased volume, geometry, and more assembly time.
So I'll pause for a second to see if anybody else has a question, but I have like 4 more. So,
Josh, can you explain exactly what you mean by capstan-based?
So a if you look at, when you go to my slides, the Bruce E video, he actually did a good explanation of capstan in this particular video here, which I'll try to see if I can get the link for. Can I get the link for it? How do I get the link for it there? I don't know how to get the link for that one. Where's my chat window? But that Bruce E link, he has a solid description of capstan, and a capstan system is basically just a winch. So you have pulleys of different diameters, and you wind one around the other. And then most of the capstan systems are designed to be bidirectional, so you can apply with zero backlash force in either direction. But they require lots of either 3D printing or machining, and then manual assembly to get all the cables set up working right for each joint. But so the winch system allows you to have a lot of reduction in a relatively compact space. And it's been used for like surgical robots as well. Like I think the Da Vinci surgical robots used capstan-based reducers as well, although they were notorious. And if you do production versions of them, they're very expensive because they take a lot of labor to produce. But if you're a hobbyist and your time is free, then they can be less expensive. So the Da Vinci one, they switched away from capstan because it was too expensive to actually produce for real, but it's still popular in the hobby world.
okay, I heard a pause, so I'm going to ask my next question.
So capstan.
Go ahead, Greg.
I was just going to add to that. My robot arm version 2 was a cable-driven robot arm, and I abandoned it for that same labor-intensive purpose. Since I take it apart, my whatever project it is, take it apart and put it together so many times, rethreading all of the cables every time I took it apart, that's what motivated me to say, I got to move on to something that I can disassemble and reassemble with greater ease. And the capstan is the pulley that gets attached to the stepper motor in my case, that drives the cable. So that's where the word capstan comes from.
I mean, yeah, capstan was like used on ships to, that was the big central thing that you'd have 100 sailors pulling on to lift up the anchor or whatever. Here, it's just the pulley that you wrap the cord around.
So we use belts that have embedded Kevlar or embedded other fibers that don't stretch very much to reduce. It's sort of a pre-assembled kind of a version of that. It reduces the amount of labor, but it's still an issue.
Yeah, and the Quad A1 does use belt drives to the knees, which similarly uses aramide reinforced belts. But belts have an effective, capstans can have a much higher reduction ratio than belts as well.
Right. And what we found is that the belts, even though the lining of the belt doesn't stretch at all, the teeth on the belt do move slightly against the pulleys. So you get some induced springiness, which isn't necessarily a bad thing if you compensate for it, but it's in there. So I'm curious how you have managed to keep all of this really advanced hobby stuff, because I mean this is like next level work. How have you kept that from being acquired and turned into closed source from a big company that just offered you a ton of money? I'm curious if are you not seeing those offers? Because I know several people that I can point your way. And then secondly, if you are seeing those offers, are you holding them off on moral grounds, or are you holding them off on I don't need the money grounds? Or it's really amazing. And just I'm coming from Haddington Dynamics, where we have an open source robot that was then acquired and taken probably closed source, although the prior versions are still open.
I will say that I haven't received any serious offers of acquiring everything. Even if I did, at this point, I wouldn't say moral grounds, but somewhat moral. I mostly, a lot of this work, I want to be able to make it be profitable so it can be my job, but I also want to make it so that it advances the state of art and lets everyone make progress. Which is why all the software is not just GPL, that's Apache license, which means you don't even have to ask my permission. Somebody could come along and take it and close source it without even asking me. They couldn't use the names are trademarked, so they couldn't call it mjbots or Modius, but they don't even have to ask me to take it closed source. And to some degree, I expect that to happen. Some roughly following like the Prusa business model of open source, but building a brand based on high quality support and high quality products, and expecting and reasonable prices, and expecting people to be able to support that. And I mean, so far it's going okay. I mean, right now with all the COVID supply chain issues, I'm not sure anyone would want to take it over, because like if you told me a year and a half ago I would have orders for 2 years out to be able to build this low volume stuff, I'd say you're kidding me. But here I am, and I have orders for 2 years out to build this low volume stuff because there's no other way to get parts.
Yeah, and a follow-up question on that is, do you have any thoughts about how to convince for-profit closed source companies that they should open source and that there is the financial benefit to that? Or do you think that for the most part there just isn't?
It's really tough. I mean, there's of course a big debate in the open source community, and a lot of companies, like even you see Elasticsearch, a lot of ones that try to stick to an open core model, eventually if they have VC funding have to renege on it, because they're just, it's tough to make a open source company where the profit comes from the open source product. In practice, if you have an open source company, your product is like Red Hat, where it's actually the support, or it's Prusa, where it's manufacturing the hardware reliably and effectively. But then for a hardware system, you then put yourself on the treadmill of competing against every Chinese upstart, which will undercut you in price by 3x or 4x. So it's to be honest, a very tough business proposition.
Well, the way that we were running Haddington, which was working and still does, is, you know, the current development is all closed source, and the next robot that we're building is, you know, something that we'll keep to ourselves and only sell to certain people. But the expectation is that as soon as the next robot gets out there in the world and people are using it and people are seeing it, somebody's going to reverse engineer it, start stealing it, and China's going to start manufacturing it. So you can undercut them by just open sourcing the old design. Here it is. It's all for free. Everybody who wants to make one, make one. And then they all go, oh, poo. And then they, you know, start trying to reverse engineer the next robot and get ahead of you. So it's a matter of staying one step ahead.
Yeah, there's one step ahead, and there's also, as I'm sure you're aware, but maybe not all hobbyists are, there's a whole lot of necessary work to produce a system which you can't get from reverse engineering, like all the production systems and the test fixtures and the QA procedures and all that things which you're going to sink the time to develop regardless whether you are starting from scratch. And for me, I'm not open sourcing those either. If you're a hobbyist making one or two, you don't care about any of that. If you're a company, you'll have to do it on your own.
Right. That's a very good point. Thank you.
Well, I think with that, maybe we'll just wrap things up. Thank you again, Josh. This was an awesome presentation, and wish you well on your continued endeavors there. Hopefully you get caught up on that backlog someday.
Will the video be available?
It will. It will. It looks like it may be 2 videos, so with the meeting and then the presentation, but that's okay split. So, yeah.
All right. Well, thank you very much, Steve.
Yep. All right. Thank you.
Thanks, Josh.
And
Awesome
Josh,
presentation,
Josh, if
I'm tethered. walls and walls of bins for parts. And I have some overflow storage in various other places that cycle between for tools and assembly. It's pretty clear that I currently do final assembly and QA of all the parts here, but like the PCB assembly is done at a PCB assembly house, and the CNC machining is done at a CNC machining house as well. It's not done in-house. But the workspace I have is just a few desks and those bins of storage, which the active ones are in this room and the inactive ones are cycled out to other storage locations.
And do you use that little desktop machining CNC there in that room or somewhere else?
It is in this room. At the moment, it is disassembled. It is right over. Can you see it there? I don't know. I have to disconnect from my Ethernet to it high enough to see it. But it is behind a box.
Ah, okay.
See it over there. And so I use it in this room as well with ear protection.
Okay. And I saw there, almost right in front of you, a press. You do it for putting bearings?
Yeah, it's just a desktop arbor press. Turns out that's the tool that I did not know I needed, but I use all the time.
Yeah, okay.
Because there's so many things that need to be pushed in or out, and that until I had a fairly equipped lab before I started doing any of this. But the arbor press was one of the tools that I didn't know I needed until I was. But once I've had it, I use it probably almost every day to put something together or push something apart.
Nice. Thank you.
I actually use my drill press to do that. I'm curious if you ever tried using a drill press instead of an arbor press.
I use my lathe.
Yeah, I mean, anything which gives you controlled torque or linear force amplification will work. I had at one point I had a drill press, but I got rid of it because the things I was drill pressing, I would rather go into the local maker space and use their mill for. And this arbor press, I normally actually keep it under my desk and I just pull it up when I'm doing stuff because it weighs like 20 pounds or something. So it's easy enough to just schlep around when I need to press something in or out. But
I'm curious about, go ahead.
Go ahead. I was just going to share other random tools that were useful, but your question is probably more important.
Oh, geez. Now I ticked somebody off who wanted to see other random tools, but they'll get back to it.
Yes, you have.
Okay, I'm sorry, Greg. I'm really curious about the safety systems on those huge farm and mining equipment. How did you keep that from ever going off the rails? And or is it that your code is always perfect and runs the first time?
Well, clearly, no. Even if you think it is, you can't assume that that's the case. But no, I mean, we adhere. There are well-defined IEC standards for developing safety for automation systems, which you follow both of the process for, and then it necessitates certain design constraints. And so for like those systems, they were all designed to work only in areas with trained people present. So that's one thing. And there are also interlocks required that you can press a button to disengage the system, or some of them had remote deactivation systems that would cut all the software out. And so there were layers of safety that you apply on, so that even if you had a mistake in the software, no people will be injured. Machinery might get hurt, but people wouldn't be injured unless like 4 levels failed at the same time. I'm certainly glossing over what we actually, we had a team of people who did nothing but work on the safety systems. So certainly a lot of effort goes into it to do it well and properly, and not just to check all the boxes, but you want to check the boxes so that, I mean, nobody wants to make a system that causes harm to someone. And certainly those big machines have the potential to do serious damage if they go awry.
Well, I'm glad to hear that there were people working on that. I think I'm more amazed by it because the last time that I worked with a really big machine, it was a crane system back in the late 1980s, and there was no safety at all. So I'm glad to hear that the industry has progressed.
I mean, but it may not have been the crane was likely intended to be manually operated by a person who could, worst case, kill the throttle or disconnect the battery.
Well, that's true, yeah. And we did have somebody supposedly always standing by. Strangely enough, the only times that anything ever really went wrong, twice, the guy who was supposed to be on safety was distracted, and it took him several seconds to react.
No, that's actually one of the key problems for the self-drive. When we worked at Toyota, if you ever listen to any of Gil Pratt's speeches, the vigilance gap is the key thing. And I mean,
Right.
I can tell you as an engineer developing autonomous systems, testing them, I have fallen asleep in the cab testing autonomous systems. It is that hard to stay awake when doing so. And so the fact that people like Tesla are expecting normal, non-trained individuals to stay awake for 6 hours at a time, monitoring the system in case a tractor trailer is parked in front of you is pretty
yeah. Oh, well, that's
irresponsible in my book.
Yeah.
Given that I know that me as a trained person can't do it for more than a few hours at a time.
That is such an excellent point, and one of the things you understand is that human beings are not designed to handle repetitive, boring tasks for long periods of time. And honestly, the more creative and better educated the person is, the more experience they have, the less capable they are to handle long, boring, repetitive tasks. You know, it's exactly the wrong person to put in that place, because those are the people who are used to constant brain stimulation. And when the whole system is working perfectly and there's nothing to stimulate the brain, they are the least capable people for that job.
Mhm.
I can't speak to that, but I can tell you that it's very hard for almost anyone to maintain constant vigilance for a 6 hour drive, looking for something with sub-second reaction times.
You know, the Air Force has spent a lot of time studying this because they have the same problem. You have somebody who wants to fly a 12-hour mission and then do some really intense things for another 2 minutes at the other end. And it's not a trivial problem to solve.
Right.